Hello and welcome back. Alright, so in the last video I kind of gave you this whirlwind introduction to trees. So we're going to take a little bit closer look on this expression tree that I was talking about. Go through the semantics on how we actually create one, without actually writing any code. And then we're going to go ahead and jump into our code editor and start pounding out some code to turn this turn our algorithm that we're going to generate into some real code so that we can evaluate expressions that people type in. Basically, we're going to create a calculator that can read in a string of input and give you back what the result of that input should be. All right, so if we take a look at our expressions, someone might give you this to solve. And so we know how to solve this pretty easily. We understand order of operations, what things should happen first. We know that we should do parentheses first, we should do multiplication first, and then we can do addition and subtraction in here. Now the idea behind an expression tree is that it stores our values over here, or it stores our values, and it stores our operators. But it stores these in such a way that there's a consistent way in which we can pull that data together and kind of evaluate what that means. So we're going to be using a binary tree, and a binary tree lends itself really well to our expression because the operators are what are known as binary operators. That is, they take two inputs all the time. So the plus operator, for example, always takes two numbers to add together. You can't say 1 plus and then be done with your expression because it's meaningless. So it's always 1 plus some other number. Same with multiplication. It's always 2 times 3. Like even when you raise exponents, right? It's always some number, and then you have the power, and then you have the power value that you're going to raise it to. So all of those mathematical operators are indeed binary. So that leads us to writing that into an expression tree really well. Okay, so what that means is that since a binary, or since an operator has this binary relationship, we're going to want to store the binary, we're going to want to store the operator as the parent node of our mini expression that we look at. So let's take another look at that 1 plus 2 example again. So that's why we put the plus as the root, and then we have 1 and 2 down here. Okay. Now you'll see that we have this multiplication here. So if we take a look at 1 plus 2 times 3, well, what is that going to actually be? We know that we're going to need to do 2 times 3 first. So when we evaluate our tree, we evaluate from the bottom up, and we go from the left to the right, just like we do in our normal expressions. We start from the left to the right and kind of figure out what we're going to do. All right, so in that case where you have like 1 plus 2 times 3, well, we're going to need to write code to understand that, you know what, the multiplication operator actually has a higher precedence than the plus operator. So we don't want to do 1 plus 2 and then times 3 on the right side like this. Here, let me draw that graph out. We'd have the times multiplier, okay, then we'd have 3, and then on our right we'd have the plus operator, and then we'd have 1, and we'd have 2, right? So if we were going to create a tree just reading from left to right on the expression 1 plus 2 times 3, you would get this tree because you'd have 1 plus 2 1 plus 2. So you write down that node set right there, 1 plus 2. All right, so now you basically have this item. I'm going to put it in brackets. It's going to be 1 plus 2 times 3. And so remember, our operators are binary, so the left side of this times 3 now is going to be that result of 1 plus 2. And so that's why that 1 plus 2 expression gets put over here as the child on the left side of that graph. And so the times is the operator, so it goes in the root, and then the operand, that number 3, goes on the right side. This is what the tree would look like if we didn't care about order of operations, and this is of course is wrong, because if we evaluated it, like I said, we started from the bottom and worked our way up, we would get 1 plus 2, and then we'd shove that in here. So we'd end up with 3, and then we'd end up with times, and then we'd have 3 over here, and then we could evaluate that, and then we get 9 as our root node, and that's our answer because there's no other nodes in our graph. Obviously that's wrong. Our answer should really be 7. So how do we represent that answer correctly? Well, that means we would have to have 2 here, the times operator there, 3 here. Then we'd have to have the plus. Then we would have the 1 operand over here on the right side. And so this is the correct graph. And so the algorithm that we use to do that is basically we use a stacks to help leverage. We'll leverage stacks in our implementation so that we can pop operands and operators on and off. So if you don't know what an operand is the thing the operator is doing its work on. So it's always the numbers in our expression. Those are the operands. So let's go ahead and walk through the algorithm to generate this graph that I just kind of drew up on the board and you all believed was correct. Alright, so let's go ahead and take a look at our algorithm here. So we're going to use the same example, 1 plus 2 times 3. Okay, so in order for us to do this algorithm, we're actually going to leverage some data types that we've already taken a look at. And that data type is going to be the stack. And we're actually going to have 2 stacks. The first stack is going to be for our operators. And the second stack is going to be for our operands. So if we jump back over real quick just to show this tree, when we did this, the operand are the numerical values in our tree. Basically the left side of our operator side of our tree. Okay. All right, so we have these 2 stacks, and our operators are going to be our operators, our mathematical operators, our plus, minus, times, divide, and our operands are going to be that left-hand side of the tree. I don't want to say it's going to be the value of the number here, because again, if we look back at the tree here, like the operand for this times, if we look at the operands for this times node, we have this expression, this 1 plus 2 expression. So that's what I want to just call it the number that's being worked on. It's the one side of that operator's data that's pulling in to manipulate. Okay, so let's go ahead and walk through this algorithm. We'll explain how it works. Well, I'll explain how it works, and then we'll go ahead and take a look at how we can actually start to implement this in C++. Okay, so the first thing that we do is we start from the left side of our string, and we see that we have an operand. Okay, perfect. So we're going to put that on our operand stack. Okay, so what we're actually going to do is this is going to be a node in our tree. So I'm going to make it look like a node. Alright, so now we see an operator. Okay, so when we see an operator, we want to check to see if there are any operators already on the stack that have a greater than, or a precedence that's less than or greater than. Okay, and then based on that, we'll do 2 different things. So there's nothing on the stack right currently, so we're going to go ahead and just add the plus operator to the stack because we don't know what we want to do yet. Okay, so now we see another operand. So our operand is a 2. So we're going to go ahead and add the 2 on the stack. Okay, so now we're going to see a multiplication operand. The multiplication operand says, hey, does the operator that's on the stack have a greater precedence than me? If it does, then I'm going to pop the operator and put that together with the two operands on the top of the operand stack, and then shove the result of that back into the operands. But in this case, the times is more, or has a higher precedence than plus, so all we're going to do is put the times operator on the operator stack. Okay, and now we're going to read in the last value, 3, in our operands. So at this point, we've read our expression. We have a bunch of values in our operand stack, and we have 2 operators in our operator stack. So it kind of looks like nothing happened. We parsed it, and we don't have a fancy expression tree yet. So this is one of the things that you need to do. If at the end of your expression you still have operands left, operators left on your stack, you need to pop those operators and combine them with 2 operands from the top of the stack, shove that result back onto the operand stack, and continue to pop the operators until the operator stack is empty. So what does that look like? Okay, so we're going to pop x. Okay, so we're going to put x into a node, and we're going to pop 2 operands, because remember, operators always operate on 2 different operands. And so we're going to put the top one on the right side, and the next one over here. All right, so this is our new operand that we're going to shove in here. So our new stack looks like this. Okay, and our operator stack over here just has a plus. So we ask the same question again. Is the operator stack empty? Well, no, it is not. So I need to do the same thing I did before. So now the interesting thing is, hey, you know what? My operands has a node in here instead of just a normal operator or a normal operand. But remember, we added our operands as nodes into our stack, so there's really no difference between these 2 values when we look at the code and how we interact with those. So what do? We take a plus, put that as the parent. We add the top to the right-hand side. So we're going to get times. We're going to get 2 over here. We're going to get 3 there. And then over on this side, we're going to get that 1. Okay, and this whole thing over here goes into the operands. I'm just going to draw an arrow. And we have no operators left. Okay, perfect. So what does that mean? That means the top item in our operands is actually the root node of our tree. So this plus is going to be the root node of our tree. And now if we want to evaluate, we do that evaluate thing. Like I said before, we do a recursive. We start at the top. We evaluate the left side. We do the operator on the left plus the right. Well, the right needs to be evaluated further. It goes down the left, hits an operand. That operand value is 2, so there's no more operators. So that's going to return 2. So now we're going to get 2 times whatever this right-hand side is. Right-hand side is going to return 3. So we're going to end up getting 6 here. And so then we're going to get 1 plus 6 is going to be 7. So that was a really 2-second explanation of how we do that evaluation. And we'll dig more into that when we actually start writing the code for it. But that's the workflow. That's the simple case of how we do the operands. How we read the expression. We'll handle the case of when we have parentheses in our code. So if we have 1 plus 2 times 3. Actually, let's just go ahead and walk through that example so you guys can see how that works. Okay, so if we have 1 plus 2 times 3. Okay, so now that result should end up getting 9, so our expression tree should look different. Okay, so let's go ahead and put our operators over here. And our operand stack over here. Okay, so we just do the same thing. Now the interesting thing is here we have this parenthesis. All right, so we have a left paren. Let's go ahead and put that on the operator stack. All right, now we get 1. Okay, let's put that, create a node, put that operand in that node, and pop that on, or push that onto the operand stack. Okay, we got a plus now. Okay, so now we ask the question, hey, does the left paren have a higher parenthesis or higher precedence than me? No, it doesn't. So put my plus on this operator stack. All right, so now we read 2. Oops, sorry. That looks like I popped the C, or the parenthesis. So we'll have the parenthesis plus now. We read a 2, so we create a node and put that on the operand stack. So that's what our stack looks like now. Okay, and now we hit a right paren. And so now, since we've hit a right paren, what we need to do is we need to pop all of our operators until we hit a left paren. And then whenever we pop an operator, we always do that. Grab the 2 operands from the top stack, create a new binary tree node, set the parent to the operator, set the right and the left to the operands that we popped off the operand stack. Okay, so we hit a right paren. We're going to pop this plus operator, okay, and we're going to join the 1 and the 2. And then we're going to pop all the way until we get to the left parenthesis and pop the left paren as well. So we're going to end up with an empty stack. I'll just draw an underline over here, an empty stack, and then we're going to end up with this as our operand that's sitting in our operands stack. Okay. All right, now we continue reading through our expression, and we're going to get a times operator. Okay, so we put the times operator on the stack because there are no operators on the stack to ask the questions of, are you less than or greater precedence than me? Okay, and now we shove the 3 onto the operand stack, and so I'm just going to put that here. All right, so we have the operand 3, and then we have the operands of this 1 plus 2 expression. All right, and so we're at the end of our expression. So now we ask that question, hey, does our operator stack still have operators on it? Yes, indeed it does. All right, I'm going to pop the operator. So what do? I pop the 2 operands, put them on the left and the right. And then I shove that back into my operand stack, just like we've been doing. All right, so we got a times node. We got 3 goes over here. We got the plus node. We got the 1. We got the 2. And so now if we go through that evaluation again, we start at the top. Okay, we start right there at that root node. Remember this went back into our operand stack. Our operators are empty, so we know that our root node of our expression is that operands item. Okay, so how do we evaluate that? We go to our top node. We evaluate the left. And then in this case, we're going to do times the right side. Okay, so the right side is actually going to give us back the numerical value 3 without any further evaluation down that path. The left side, however, hey, you know what? We found another operator. So what we need to do is we need to do the left plus the right, shove that here, and return that back up to the question on what the left side of my tree equals. Okay, so that's going to be 1 plus 2. So we're going to put 3 here. 3 is going to go up. 2, 3 over here is going to go up. And we're going to end up with the result of 9. All right, so that is how the expression tree works. That is really all the special cases we need to handle. We can do an entire expression tree right now. So actually, if you feel up to it, I go ahead and challenge you to not take a look at the next couple of videos where we actually implement the tree and see if you can do it just based on watching these 2 videos. All right, thanks.